Lord, these slides keep going on and on. Maybe this is the last one. Maybe there's 20 more of these. All right, analysis of variance XII. What's that, 13? Revisiting correlation and regression. So this really isn't about Anova. It's about talking about hypothesis testing in the context of correlation and regression. We didn't talk about hypothesis testing when we talked about correlation and regression because we hadn't had our section on hypothesis testing yet. That's, you know, different people design their courses different ways. I don't like to be doing hypothesis testing in the third week of class. I think it's a little early, it's a little rushed. So I structure my class so that we talk about correlation and regression, and then we circle back on hypothesis testing for those techniques. All right, hypothesis testing for correlation. With correlation, we do have a null hypothesis. And that null hypothesis is simply that rho, the Greek symbol rho, which is the symbol for the population correlation, is 0. Very consistent with the other null hypotheses we found, that where we say no difference, no effect. Here, no correlation. Null hypothesis is always no something. So we're testing the null hypothesis that in the population, the correlation is 0. We reject the null hypothesis when our probability is less than alpha, just like every single test that we've looked at. It's all the same. So once you know one thing about hypothesis testing, you actually know a lot of things about hypothesis testing. So here's an example of in our stress and symptoms that we saw before. We see that the probability is very low, well below 0.05. We also get a confidence interval here, which excludes the value in the null of 0. So we could reject the null hypothesis in that case. For the self-esteem and happiness example, we see a result where we can't reject the null hypothesis. 0 falls within our confidence interval. And the reason why that was, even though that was a really large correlation, was it was a small hand calculation example. We only had a small sample. Generally, if you've only got 6 or 7 scores, you're not going to be able to reject hypotheses. You just don't have enough information. And here you might report it like this: greater stress related to reports of more symptoms. R with 105, that's the degrees of freedom, is equal to 0.51. Probability reported as less than 0.001 whenever the probability is very low. Similarly down here, really the only thing that differs is the probability is reported as a specific value when it's greater than 0.001. And again, we talked about using the 95 confidence interval already, just some slides to review that. 0 is not included in the first one, it is included in the second one. Again, those confidence interval approaches always going to give you the same results as the ones using hypothesis tests. Taking a look at what you would see in the literature, I think I have a couple of things in this section from my own papers. These are usually presented in a large matrix as a precursor to doing other analyses. Here's a study I did about how people's attitudes toward affirmative action change after college diversity experiences, having instructors of color, having ethnic studies courses and things of that nature. And we can see we've got all of the correlations between all of the variables. There's 11 variables in this study, and I just presented a matrix with all of those correlations there. The little stars, as we've seen before, represent whether we could reject the null hypothesis or not, whether there was a significant relationship. 1 star generally being used to denote less than 0.5, 2 stars generally being used to denote less than 0.01. And then sometimes 3 stars to denote less than 0.001. All right, hypothesis testing for multiple regression. Multiple regression provides us with 2 different types of tests that get a hypothesis, that we apply hypothesis tests to. The first one is a significance test for the R² value. The null hypothesis is, big surprise, that the R² value in the population is equal to 0. That's noted as rho squared equal to 0. And again, we reject it when the probability is less than 0.05. The significance test for a slope. The null is that the population slope is equal to 0. That would be noted as beta is equal to 0. Again, no slope. We reject the null hypothesis when the probability is less than 0.005. For the R square value, we're going to have one test. For the coefficients, we're going to have, or the slopes, we're going to have one test for each predictor variable. Here's the data from the Black Lives Matter example we looked at earlier in I think the regression section. You can see we get a probability value. We have one that's well below 0.05 for positive contact. More positive contact with African Americans relates to more positive feelings toward Black Lives Matter. Negative contact doesn't meet that 0.05 criteria. Realistic threat doesn't meet the 0.05 criteria, so no relation between negative contact, realistic threat, and support for Black Lives Matter. And then finally, symbolic threat. We have a negative relationship, and it's below the 0.05 criteria, telling us that greater feelings of symbolic threat from African Americans lead to less support for Black Lives Matter. For the multiple R squared value, we'll see it's 0.1876. Probability there is well below 0.05, telling us that our set of predictors, those four things together, something in there is allowing us to reject that null hypothesis. So that's just attributable to all four variables together. The individual coefficients are where we tease out what actually was important. All right. More examples from the literature. I think this is from the same study we just looked at. Often these are reported in the table form with many predictors, often presented for several analyses. So you might see 3 or 4 multiple regression presented. You might be looking at the same predictors tested on multiple dependent variables, on multiple groups of people. That's what I did in this study. I had white students, African American students, and Asian American students. Not that students of other ethnicities didn't matter. They just weren't very many in the University of Michigan data set at that time. There's for 2 different dependent variables tested, quality and differential criteria. We've got an R squared total for each of those. All of those we can see from the little stars came up as less than 0.05, telling us that our set of predictors explained support for affirmative action in terms of these 2 different measures. In terms of these 2 different measures, they were explained by the set of variables. Just taking a look at the predictor that I was most interested in, all of the predictors were established predictors that people knew were related to support for affirmative action. What I brought to the table was this diversity, appreciation for diversity, or experience with diversity in this case, a variable. And what I was able to show is that we've got a significant coefficient or a significant slope, the terms we've been using in this class, significant slope for each of the variables. For white participants, for African American participants, and for Asian American participants. In every case, greater participation in diversity events related to more support for affirmative action, more support for diversifying the university further. And if I'm not mistaken, this is the last slide, and we have reached the end of Anova.